Recording in progress.
Okay, I hope the sound works for this recording. And as promised, I'm going to do a redo of the Burges lecture that I provided a couple of weeks ago, and there was a request to do a recording. We are here in the lecture hall, but nobody's here except of Jessica. So it will be just almost a pure recording, and there's also a Zoom sharing of this, but nobody's in the Zoom room either, unfortunately. So I will just record it now for anybody who wants to watch this after, and hopefully you get in contact with me, and we can have some discussions about this. For the Burges lecture, because I wanted to make it a little bit provocative, I chose the title "Engineering the Natural and Built Environment from Today's Knowledge into Future Visions," whatever that means. You can reflect about this title. My interpretation of my own title would be that's what engineers do, right? So we want to basically create a better future and create designs that bring what we have now into a better future, and that holds for all the engineering disciplines, but especially for us natural and built environment engineers. Just a couple of words about myself. Because in the Burges lecture, I even had a formal introduction. Here not, but just briefly, you know my name. I'm a German Bauingenieur, that's a civil engineer with a diploma. This was the old German masters. But I also did a master's of computational mechanics, all at the TU Munich. So I have a little bit of a background in mechanical engineering as well. Then in 2008, I had the chance to start in 2004, I had the chance to start my PhD that I finalized in 2008 at Stanford University. And so being a very computer-minded person at Stanford, I started doing a lot of computer science, but then realized that, to change, we also need to understand organizations. And at the end of my PhD, I did a lot of classes and focus on organization science. Then I went to the Netherlands, worked 8 years in the Netherlands, went to the tenure track from assistant professor to full professor at the University of Twente. And then 2016, I think 16, I'm at the Technical University in Berlin, Technische Universität Berlin. I have the chair for civil systems engineering there, and this is kind of our group. So we exploded in the last 5 years. At the moment, we are working with 3 postdocs, 10 own funded PhDs, a lot of external PhDs just basically enrolled in our PhD program. It's nice in Germany because in Germany we don't have tuition. So we have a lot of people who can just study with us, a whole bunch of master student assistants that we finance. We have our own international master's program in civil systems engineering. So if you have interested bachelor students, send them our way. And we are mainly funded by large European Union projects, the BIM Speed project, ASHWIN, the CBIM project, the Reincarnate project. Just brief overview about some of the research topics. One is energy efficient building renovation. I'm not going to focus too much on these, just giving you a little bit of background where I come from. Work on asset management infrastructure, condition assessments. We even have a PhD student who builds robots, wall climbing robots. We have a small scale robotics lab that we built up to image recognition work. One of our key research areas is what we call integrated concurrent or also collaborative engineering, ICE. Digital twins. We look into digital twins for the construction site, but also for buildings, for the energy simulation and so forth. We have projects in factory design and engineering, working, for example, with Volkswagen. And then we have lately even did win a large European project looking at the circular economy for the built environment. And then something maybe a little bit for the future, but we are also starting to look at space station engineering, not yet really funded, but we believe that civil engineers should also be integrated in that. We know how these things should work, right? And yeah, the things, now coming to the serious part of the presentation, the things that keep me or us up at night is kind of this. And there's, I read a lot of science fiction, and one of my favorite books is 2312 by Kim Stanley Robinson. And in this book, he talks about, there's a passage where a historian in the future, in 2312, looks back, right? And what historians do, they talk about epochs, right? So Stone Age and Iron Age and whatever. And she describes the epoch that we are living in now. She calls it the dithering, which is from 2005 to 2060, basically from the end of the postmodern to the fall into crisis. And so Charlotte, who's the historian, derives the start of this epoch from the UN announcement of climate change, which was, and that's, I think, always shocking to hear, and that's why I repeat it all the time, in 2005. Charlotte says these were wasted years, right? And then the next epoch after that was the crisis. She calls it the crisis, 2060 to 2130. Disappearance of Arctic summer ice, irreversible permafrost melt and methane release, unavoidable commitment to major sea rise, right? The perfect storm fashion, average global temperature by 5K up, sea level rise by 5 meters, food shortages, mass riots, catastrophic deaths on all continents, immense spike in the extinction rate of other species, and then bring it back to space, early lunar bases, scientific stations on Mars as well. Right, and this is actually not a scientific map, but this is a map. I really like this map. It's from a science fiction writing blog and fantasy writing blog, where somebody overlaid the predictions of what would happen with seawater rise. So you see large parts of our land is missing, overlaid it with temperature. So what you see here is the wet bulb temperature. And so if the wet bulb temperature is over 35, so it's a combination of high humidity and temperature. That's the dangerous thing, because if the humidity is high, we can't sweat. And then, yeah, from 35 degrees on of wet bulb temperature, humans will die. And so this is colored on the land that is left, right? This map colors the regions according to, you know, the hottest period of time that is to be accepted. And so we see that a lot more spaces on this world will not be livable. So we will not only lose space because of the seawater rise, which is like a lot of in the discussion today, but we will lose much more spaces because areas, large areas in this world are going to be no longer, or will be too hot to live in, too hot and too humid. This is a nice newspaper article, and I enlarged the date here. This is from 2013. Again, talking about, you know, the dithering, wasted years, right? So old stuff that I'm showing on purpose. And this is just a newspaper article how Berlin would look like where I live now, right? If you know, we have the permafrost melt and everything, right? So even when you think, okay, Berlin is not even at the sea or the ocean, but, you know, large parts of Berlin would be underwater if civil engineers don't build cool structures, right, in that sense. And then, you know, this is also from an old report. This is not the most recent EPC report, but actually what each of these reports show is that the previous predictions predicted things to go much slower, and everything actually goes much faster than we thought. So what will be one of the things that we, as I call it, not civil engineers, but natural and built environment engineers, need to do in the years to come? We probably will be very, very busy with increasing the resilience of places, right? Be it protection against water, be it protection against heat, so that people can continue living. Now, looking at this, how are we doing today on our projects when we look at large engineering projects? And this is a nice case study that we were able to follow in the Netherlands. It's the duck park. It's called the roof park. It's a major flood defense, multifunctional flood defense project in the city of Rotterdam. So the Netherlands, Rotterdam, Amsterdam, they call it the Randstad, is one of the most densely populated areas in all developed countries, right? And so they built this flood defense in the middle of a city. It's still one of the lighthouse projects in Europe. Last year, I read a newspaper article about this project as one of the, lighthouse projects in Europe, how you should build flood defenses, and in a German newspaper, right? And we don't like the Dutch so much. But when we looked at this project, and we were able to follow this project, and down there, and this is something that struck me back then, and motivated a lot of the work we do now. From the first project idea in '98, so I always say first project idea, probably the city of Rotterdam realized that they need to reinforce the dike because it gets too dangerous, right? Till the construction in 2012, 14 years. And looking at all the predictions, the question is, do we have 14 years to really create resilience, or the resilience we need? Right? I don't think this is a special project. I think this is a project that went very well, right? Lighthouse project. So 14 years is more the norm, right? So we have probably a lot of projects that take a lot longer, right? Another thing that worries me, I put it provocative, are we our best customer? So when we look, right, who's causing the climate change? Probably civil and built environment engineering is responsible for more than 50%. Right, so we have the building operations that are 28%. It's just one chart, right? There's so many and all different numbers, but I think they all converge to like the same thing, that it's more than 50%, right? All the material production, concrete, steel, aluminum, which mainly goes into us. And then there's this 23 bulk of transportation. And then we're also working with Volkswagen, right? For example, industry, right? Where, civil engineers probably also have a say, can do things, right? So we also not only need to create resilience, and we need to become much, much quicker to do so, but we also need to save resources. So we are the engineers that will be mainly responsible to save resources, right? To maybe mitigate at least the speed, but hopefully also the magnitude of the climate change effects that we're expecting. This is just a nice picture from the Circularity Gap report in 2020 that shows a little bit building up on this theme where the resources go. So every year we extract 92 gigatons, we only recycle 8.6 gigatons, right? And we see we emit 14.8 gigatons, or maybe important is we look at housing. In housing goes 38.8 gigatons. And that's building new houses, right, of the extracted materials. And then, of course, again, we have mobility, communication, healthcare, which I think a lot of the resources we extract go into these fields are also for buildings or infrastructure, right? Services. And then, of course, nutrition is a big part, right? And then we emit this, we disperse this. We add to the net stock. That's what we do, right? So we actually take these things and add them to a net stock. It will stay there. So this is a yearly picture. So we'll go maybe back into emissions dispersants, or hopefully also recycling after the lifetime. Hopefully not 30 years, what we plan now, but maybe 100, 150 years. So in the end, it's not so bad what we do, but we still need to, still significantly work on emission and dispersion, obviously, but also, if we can reduce this as well while providing, the housing we need for the world, then it would be good. Big research question that follow from this that we have at the Civil Systems Engineering Department is, how will engineers have to design, build, and maintain the natural and built environment? How do we deal with the systemic complexity and the life cycle focus that we need to develop? How do we integrate the social and technical innovations? I think the social part is very important. I like this English term, civil engineering, that speaks to it. We create the engineering solutions for the civil society. So more than all other engineering disciplines, we need to integrate and look at the social and how to also move the social in relation with like our products forward. We probably need to involve specialists from many different areas. And we also need to take care of public participation. And then another big research question we have is how we will use computers to do so. So this is actually a picture that I found from the history of computers. So the job position of these ladies was called computers in the 1960s. Right? Unfortunately, they were all ladies, but that's what it was. So, you know, the engineers, which were men back then, were designing something, had some calculations, some equations to solve, and then they gave it to the computing department, and the computers were actually humans still, they were calculating. There's a really cool book, if you are more interested, it talks really nicely about this. It's Calculating Stars, which is the story of one of these computers that becomes an astronaut. But in the end, of course, we have like large progress in this. So computing means something completely different than it meant 50 years ago. So one of the big questions, can we use the computer to make this better that we have? See the big potentials if you do it right. Big potential, yeah, but then we'd like to make the difference between digitization. So digitization is for us really just changing from the process that we have now, into a digital form. But we see that if you want to really leverage the power the computer offers, you should think in the sense of digitalization. So can we really significantly change the business model, create new, I don't like the term revenue, but maybe value producing opportunities, right? And changing the way we do it, right? To really digitalize, we believe that engineers need to go through two mind shifts from what they were doing or how they engineered systems in the past to how they need to engineer systems in the future. And I think these two mind shifts are like the core of most of the research we do at the Civil Systems Department in Berlin, but also of our teaching in our international master's program. And the two mind shifts, the first one has a lot to do with data and how we deal with data and information. And so this is kind of on the left-hand side is a depiction of how we dealt with data and information. Back when we were building the big railroad to the US, right? So still one of the biggest or one of the coolest civil engineering projects, I guess, of all times, building a railroad to this country here. And at that time, we didn't know anything, right? There was just a wide map of anything in between. So we had the surveyors who were the big heroes back in the days. Right, we even have German young adult books talking about surveyors in the Wild West, right? And they were just, measuring, and then they built a little bit of railway, right? And then they continued, and then we're seeing, oh, we need a bridge, and then they started designing a bridge on the spot, right? So didn't know much and just engineered as they went, right? And now, of course, we digitized this practice. So we have all these great GIS tools and data visualization and so forth, but this, like how we engineer is still the same, right? But maybe we need to start, because the data gets more and more, and it gets really hard to integrate it to our processes. Maybe start more thinking, and this is a picture that I stole from like Silicon Valley presentations of Facebook and so forth. But the thing is, we have a great product. We have people who use the product, and these people create data, right? And then this was like kind of, with the data we can improve the great product. But then all these social media and Googles and so realize that they have actually too much data, and so they can't improve the product because they have an information overflow situation, and so they need to use artificial intelligence tools to make sense of the data to improve the product, right? And so I think that will be one of the mind shifts that we need to go through as engineers, is really starting to think of how do we deal with information, and learning how not only use the computer to visualize that information, but also how to automatically extract meaningful things. And maybe this is more. These are just like some random graphics of artificial intelligence, machine learning visualizations. Maybe that's much more what the engineers in the future will deal with than these maps and GIS platforms and so forth. The second mind shift that we believe needs to happen when you want to work with computers has a lot to do with how we approach the design process. And this is actually a picture on the left-hand side again that it's an Arab sketch that I got somewhere. I don't even remember. But this sketch is actually really nice because it depicts how engineers work since, I don't know, 5,000 years. So they first create a sketch of how the thing should look like, right? That's here in the black. And then in the second go, they start thinking about the logic of this, right? And what actually is it what we need to design, right? What is it what we need to engineer, right? The roof height, the height of the stadium, and the cantilever, right? And the depth of the truss, not the truss. And now we digitize their practice with our BIM tools and 3D model tools, but the process is still the same. We start first like drawing the geometry, how does this thing look like, and then we think about the logic behind it, right? And to really leverage the computer, I believe we need to turn this around, right? So maybe engineers in the future will need to start the engineering process much more trying to understand what the design problem is and how to formalize the design problem and the structure of the design problem instead of like jumping directly to engineering solutions, and get much more skilled in that process, because then they can use the computer to automatically generate these solutions for them. And then they might again deal with like these visualizations where every point is just one design option, right? And they can really not only compare maybe 3 options, like on the good projects we have today, we do maybe 3 options, but most of the time we just come up with one, right? But then really coming up to options that help us to really find optimal solutions, solutions that really lead to more sustainable buildings, and maybe also do things much, much faster with this approach. So with these 2 mind shifts, what does the next generation of civil engineers need to know? Just provocative, but just putting this out here in this talk. One important aspect is systems engineering. Of course, I wouldn't say anything else because I'm chairing the systems engineering department. But leading to, I called this provocations for this talk because I said I'm gonna be provocative, right? So leading to the first provocation, fundamentals of civil and natural, there's a typo, built environment engineering have changed, so we need to change how we teach. So we need to stop teaching analytical methods and teach numerical methods. We need to stop teaching deterministic methods. We need to stop that and start teaching more stochastic methods. And because we have the computer, and the computer provides also an education, a really great tool and toy, we need to move from paper-based toy problems, also in our tests and assignments we do, right, in the civil engineering, to computer-supported, more realistic projects. And that all supports the change that we need to have. That might be, I have this great book, Engineering Systems, by De Weck and colleagues from MIT, right? Because engineers used to talk about things like force, shape, size, tolerance, modulus, voltage, temperature, precision, construction, speed. But of course, today in practice, right, they are more likely to talk about scale, scope, state, complexity, integration, architecture, resilience, evolution, affordable, and social context, right? So maybe we need to change how we teach as well, significantly to move towards a better practice. Couple of basics that we teach, students need to understand systems. We teach this in three three different views on the system. We'd say there's functional view on the system, there's a structural view on the system, and the hierarchical view on the system. The structural view is, what we do traditionally in engineering is like creating like partial differential equations, but don't try to solve them analytically any longer, right? Trying to understand how the physical world behaves in relation of, our predicted products that we want to put in the world. And so our students probably would need to understand this on a much deeper basis again, and also integrating these models, right? We see here with like structural integration, with building physics integration, and so forth, to come to integrated designs. Then the functional view is basically we have an input and directly go to the output. So we don't want to understand what's in the system, right? That's the statistical modeling approaches, the machine learning, the AI, in that sense that we need to teach much more. And then there's a hierarchical view, because all of this needs to be done on different scales of our systems, from large scale, maybe urban planning, maybe national planning, all the way down to maybe designing single products that go into our buildings and our systems. Right? So we need to also understand, this hierarchical view. And of course, the structural and the functional view can be applied on each levels of your hierarchy, right? And then engineers need to start thinking about the combination, right? So can we develop parametric models where we can join structural views with functional views and so forth, right? To get to results. To start thinking about data-driven engineering modeling, where we have input parameters, we develop functional models that simulate something, we get output distributions, we analyze the sensitivity of the output to the input, improve our models again. Right? And this is an overview I created once for a paper that kind of shows like this input output, the different structural levels in relation to the engineering tools we have at hand. And again, we try to teach this much more explicit again in our International Masters of Civil Systems Engineering. I'm not sure what happens here at UW, right? But I believe we need to make this much more explicit again to our students, that they can really understand the engineering design process on a much higher level than they do now. And then one of the other important skills that we see is that engineering students need to start be able to deal with the design space, like moving from problem formulations to alternative generations and experimentation. That's a skill that they need to have. That's a skill I think we can teach at universities. And again, we do a really bad job at TU Berlin to teach this. Right? And maybe something to reflect about how it goes here or in other places. And then, when students can do all of this, they might be able to really do large-scale design explorations, design and engineer higher quality systems that we need, right? And hopefully also do this much quicker. Skipping this, and this is just an overview figure that we always show, like the 4 leading areas of the Civil Systems Engineering Master's Program that we designed at the TU Berlin. We say all our students will need to really understand how to model complex systems, not only like in the product modeling, BIM modeling sense, but also in the physics, partial differential equation-based modeling and risk-based modeling approaches. They need to learn how to integrate different models, not only the multi-physics models, but also the social. They need to have a good ground foundation in data analytics and machine learning to deal with the large amount of available data we have. And all of these 3 areas really need to lead to creative, collaborative, and concurrent engineering. So this is the basic philosophy of our master's program. moving away from education a little bit to industry. So we perceive that we are in a very tight race in industry at the moment. Because of course, a lot of players and actors moving also into this direction. And so this is from the JLL business report from 2018. So we see a lot of venture capital coming into the industry. Coursera is no longer there. But that was always the poster child of the venture capital. They're interesting. Had some talks while I was here at UW with former Coursera employees, so that was good about different things. But for example, I would have liked to invest it in Uptake when we see the latest valuation and the total funding amount that they got. But basically, like our industry and our traditional organizations in the industry, of course, getting a lot of pressure from these organizations at the moment. We were working with Arcadis for quite some time to shape their digital strategy. And one of the great things we did, or not we, but there was Julian, who was a really genius, who was leading that effort. At one of the first things, he went into the board of directors on Arcadis and gave everybody a sheet of paper with 2 questions to answer, individual, no discussion or something. So how much business do you think you will lose with digitalization and digitization, and how quick? And so they asked each individually and then averaged the numbers, right? And so each individual means, there's also the chief financial officer sitting there, very conservative. He doesn't believe in computers, right? Other than SAP or Oracle, right? There's also the token woman, right, in that board of directors who's responsible for human resource, right? Who doesn't like computers because that means a lot of training programs and changes and problems, right? So a lot of conservative people too, but on average, the board of directors expects that they will lose 50% of their business due to digitalization. I didn't put the number in the next 10 years. So it is a company, I think, of 25,000 people working worldwide. So their board of directors thinks that if they don't do something, they will only have 12,500 in 10 years. That's kind of. So this is people might know this, most of the people know this report from McKinsey that puts construction all the way down. Real estate is there, which is higher up, right? So it's always questionable, right? We are probably in a lot of these industries also involved, but we are always depicted to be at the bottom. But I think we need to still change quick, or the others will take over more and more business. And so the big provocative question I asked at my Burges talk, and I'm doing this recording again, sitting here in the center of Microsoft and whatever, right? But do we really want Intel, Microsoft, Google, Autodesk to engineer the natural environment? Right? Would that be a good thing? Or do we really do everything we can to change the business very quickly? And that also means changing how we teach fairly quickly, right? Couple of words at the end about science and research. My provocation number 3, civil engineering research is not relevant as we do not understand well enough how engineers creatively develop innovative solutions. So that's something I strongly believe, that we have a huge detach of a lot of the research we do. I see this, I'm chief editor of Advanced Engineering Informatics, one of the journals we have in the field that focuses on computational solutions, and a lot of the work is not relevant. I have to say, what we do want to do in this journal is we want to report progress in the engineering discipline of applying methods to engineering informatics. We want to have engineering relevance and provide the scientific base to make engineering decision-making more reliable, spontaneous, and creative. Right, so demonstrate the science of supporting knowledge-intensive engineering tasks with computational solutions, right? Validate the generality, power, and scalability, be explicit representation and use of knowledge. That's very important, I think, for our research right? And use examples of automating and supporting knowledge-intensive tasks and artifact-centered engineering. And so this is all what we want to achieve. But when we see by large what we have in the publications, it's really, really baby steps in all of these, right? But I believe these points is what we should strive forward in engineering research, not only when it comes down to computation, but I guess most of the research we do in civil engineering is developing new design engineering methods, right? And of course, using the computer to do them nowadays, right? We do also some product design, I guess, which makes some impact. But if you're working on methods, these are points probably to reflect on whether we are really doing this well in our research. And my claim is no, we don't do it at the moment. And the big research questions that we have at Advanced Engineering Informatics and also at our department in that case is then how can engineering knowledge be formalized using computational modeling methods? So not our knowledge as researchers and academics, but really the knowledge of practicing engineers, of experienced engineers. How can we formalize that? And how can we really come to a science? And science means providing evidence, doing data-based or collecting data to answer this research question. So how can computational models support complex engineering work? So not only to develop a new model and saying, hey, I'm super smart academic and this model is the best in the world. That's for me not really scientific, but really asking, okay, what is the knowledge that this method really formalizes? And is that really top of the edge engineering knowledge also from practice, and then showing that the model also works, right? And then the questions come up, of course, what is convincing evidence to answer these two research questions? Because we are scientists, so we need to provide evidence for things. Well, it's not just Timo can say that it's good, but it should be something that's not coming from me, right? And how can these questions be answered in general? Right, so how can we increase our understanding bit by bit how computational, non-computational methods can be used beyond single applications? And so that leads to the provocation 4. I guess we need to also start not only working on new ways to represent modeling engineering problems, but also need to draw on resources from social sciences to learn whether our models really help in practice. And then I want to close this presentation with basically pointing back to where I started. We are in the dithering, right? And we need to work on making engineering much stronger and much better, so that we don't move so harshly into the crisis in the future. And for me, a lot of the things of how we can improve is really reflecting and improving how we engineer the natural and built environment. Or we just move to space and don't deal with all these problems on Earth any longer. So here's, I put this up for the discussion, for the recording here, probably not, but you can move to the last slide and see the 4 provocations again. And with that, I close the recording of this Burges talk, and hope you still provide me some offline feedback. Oh, I see 2 people joined us online now too. Maybe we can have a short discussion even. But I will stop the recording for now. If I know how to stop.